Thermal properties are fundamental characteristics dictating how materials interact with heat energy. These properties govern the way substances absorb, store, and transfer heat, influencing their behavior in various environments. Understanding them is key to predicting material performance. Our focus today will be on a material's ability to either conduct or resist the flow of heat. This distinction forms the basis for countless engineering and design decisions. The efficiency of energy transfer is often determined by these intrinsic material qualities. The importance of thermal properties is evident across a wide range of applications in our daily lives. From the macro scale of building construction to the micro scale of electronic components, controlling heat flow is paramount. They underpin modern technology and sustainable design. Consider common household items like cooking utensils, where heat needs to transfer quickly to food. Or think about energy-saving buildings, meticulously designed to minimize heat loss in winter and heat gain in summer. Both scenarios rely on specific thermal properties. The two key concepts we will explore are thermal conductivity and thermal insulation. While seemingly opposite, they are two sides of the same thermal coin, describing a material's propensity for heat transfer or resistance. Thermal conductivity defines a material's intrinsic ability to transfer heat through its bulk. It is a measure of how readily thermal energy can move from hotter regions to cooler regions within the material. High conductivity means heat moves swiftly. Materials exhibiting high thermal conductivity are known as thermal conductors. These substances allow heat to pass through them with minimal resistance, facilitating rapid energy transfer. They are essential where quick heat dissipation or distribution is required. Conductors are characterized by their readiness to allow heat energy to flow unimpeded. Their internal structure is uniquely suited to transmit thermal vibrations and kinetic energy efficiently from one particle to the next. Metals are classic examples of high thermal conductivity materials. Copper and aluminum are particularly renowned for their excellent heat transfer capabilities. These metals are ubiquitous in applications demanding efficient thermal exchange. The mechanism behind high thermal conductivity in metals is fascinating. Their atomic structure facilitates incredibly efficient energy transfer compared to other material types. This structural arrangement is key to their conductive prowess. Heat energy is primarily transferred through two mechanisms within conductors. Firstly, the vibration of atoms and lattice structures plays a significant role. As atoms gain kinetic energy, they vibrate more vigorously, transferring energy to adjacent atoms. Secondly, and crucially for metals, the movement of free electrons contributes significantly to heat transfer. These delocalized electrons can rapidly carry thermal energy across the material, acting as highly efficient heat carriers. This electron mobility is why metals excel. Applications for materials with high thermal conductivity are numerous and diverse, specifically wherever rapid heat transfer is desired. Their ability to move heat quickly makes them indispensable in many technologies. Cookware, such as frying pans and pots, exemplifies this application. The base of a cooking pan must efficiently transfer heat from the stovetop to the food, ensuring even and rapid cooking. Copper or aluminum bottoms are chosen for this reason. Heat sinks in electronics are another critical application. Components like microprocessors generate considerable heat, which must be dissipated to prevent overheating and damage. Heat sinks, often made of aluminum or copper, draw heat away effectively. Radiators in vehicles and heating systems also leverage high thermal conductivity. They are designed to quickly transfer heat from a hot fluid, like engine coolant or hot water, to the surrounding air, preventing system overheating or warming spaces. Thermal insulation, in contrast to conductivity, refers to materials with inherently low thermal conductivity. These materials are specifically designed to impede or resist the flow of heat, making them poor conductors. They act as thermal barriers. The defining characteristic of thermal insulators is their ability to resist the passage of heat. They do not readily allow thermal energy to move through them, thus maintaining temperature differences across their boundaries. Insulators effectively trap heat within a system or prevent it from entering. Their primary function is to minimize heat exchange, creating a thermal boundary that keeps warm things warm and cool things cool. Common examples of thermal insulators include wood, plastic, and air. These materials are widely used in construction, clothing, and packaging due to their excellent heat-blocking properties. Each offers unique insulating benefits. The mechanism by which insulators resist heat flow differs significantly from conductors. Insulators generally possess atomic structures that lack the abundance of free electrons found in metals. This absence greatly reduces electron-mediated heat transfer. Consequently, the primary mode of heat transfer in insulators is through lattice vibrations, which are far less efficient. The atoms are more tightly bound or spaced, hindering the rapid transmission of kinetic energy from one to another. This less efficient mechanism for transferring thermal energy means that heat movement through an insulator is significantly slower and more difficult. The material acts as a bottleneck for thermal flow, effectively slowing its progress. The importance of thermal insulation is crucial for preventing unwanted heat loss or gain in a multitude of systems. It is fundamental to energy conservation and maintaining stable temperatures in varied environments. From keeping beverages hot in a thermos to protecting spacecraft from extreme temperatures, insulation plays a vital role. It is an indispensable technology for comfort, safety, and energy efficiency across industries. To quantify the effectiveness of an insulating material, we use the concept of thermal resistance. This metric provides a standardized way to compare how well different materials impede heat flow. It's a critical parameter for engineers and designers. The R value is the widely accepted metric for thermal resistance. It represents a material's ability to resist the conductive flow of heat. A higher R value indicates a greater capacity to block thermal energy. Interpreting the R value is straightforward. A higher R value indicates a greater resistance to heat flow. This means the material will allow less heat to pass through it over a given period under specific temperature conditions. Therefore, a higher R value directly translates to a better insulator. When selecting insulation, maximizing the R value for a given thickness or application is typically a primary goal to achieve optimal thermal performance. Thermal resistance, quantified by R values, is extensively applied in building construction. It is a cornerstone of energy-efficient building design, directly impacting heating and cooling costs. Common insulation materials used in construction include fiberglass, foam boards, and cellulose. Each material offers distinct advantages and R values per unit of thickness, allowing for tailored insulation solutions. The primary purpose of using these materials is to create a robust barrier that minimizes heat transfer between the interior and exterior of a building. This barrier is essential for maintaining comfortable indoor temperatures year-round. The benefit of effective insulation is profound. It significantly reduces energy consumption for heating and cooling. By preventing heat loss in winter and heat gain in summer, buildings require less energy to maintain their desired internal climate. This contributes to lower utility bills and a reduced environmental footprint. The choice of material for any given application is fundamentally dependent on the desired thermal behavior. Understanding whether to promote or prevent heat transfer guides the selection process, optimizing performance and functionality. This decision is central to engineering design. Consider the example of a frying pan, a common kitchen utensil that perfectly illustrates application-specific material selection. Its design intelligently combines materials with differing thermal properties to achieve its function. The body of the frying pan is typically made from metals like aluminum, copper, or stainless steel. These materials are chosen for their high thermal conductivity, which allows for rapid and even heating of the cooking surface. Efficient heat transfer is paramount for effective cooking. Conversely, the handle of the frying pan is made from materials with low thermal conductivity, such as plastic, silicone, or wood. This prevents heat from traveling from the hot pan body to the user's hand, averting burns and ensuring safe handling. Another excellent example is a refrigerator, a ubiquitous appliance designed to keep food cold. Its operation relies heavily on the strategic application of thermal insulation to achieve its primary function. A refrigerator utilizes insulation within its walls, doors, and freezer compartments to effectively trap cold air inside. This insulating layer forms a thermal barrier, separating the cold interior from the warmer ambient room temperature. This insulation prevents heat from the outside environment from entering the refrigerator's cooled interior. By minimizing heat ingress, the refrigeration unit needs to work less to maintain its low temperature, thus saving energy and preserving food quality. Understanding the thermal properties of materials is absolutely vital for designing energy-efficient systems across all sectors. This knowledge allows engineers to create solutions that minimize wasted energy and maximize operational effectiveness. It is a cornerstone of sustainable design. This comprehension is also critical for optimizing thermal management in electronics. As devices become smaller and more powerful, dissipating heat effectively becomes a major challenge. Proper material selection prevents overheating, prolongs lifespan, and ensures reliable performance. Furthermore, leveraging thermal properties is essential for creating comfortable and sustainable living environments. From insulating homes to designing efficient heating and cooling systems, these properties directly impact our daily comfort and environmental footprint. Ultimately, the overall goal of studying thermal properties is to effectively control heat flow and harness its potential for human benefit. Whether channeling heat, blocking it, or converting it, a deep understanding empowers innovative solutions for a better future.